Hello and welcome to another video brought to you by Group 4 Zinc of Retail Uden. We're now going to discuss about the colligative properties of a solution. A colligative property mainly depends on the amount of solute and solvent, or the concentration of a solution. In this video, we're only going to talk about three of these properties: the vapor pressure lowering, the boiling point elevation, and the freezing point depression.
Vapor pressure lowering is a colligative property wherein vapor pressure is the one exerted by a gas in equilibrium under given temperature at a closed system. This means that when we add more of the solute, which is non-volatile or not likely to evaporate, in a solution, the solvent will have a lower vapor pressure. We can refer to François-Marie Raoult's equation in vapor pressure, or simply Raoult's law. P sub A is equal to X sub A multiplied to P null sub A. P sub A denotes the partial pressure of the solution alongside the solute. X sub A is the mole fraction of the solvent. P null sub A is the vapor pressure of the pure solvent. Let's look into this example. The vapor pressure of pure water at 115 degrees Celsius is 1085 torr. A solution of ethylene glycol and water has a vapor pressure of 1.30 atmospheres at the same temperature. What is the mole fraction of ethylene glycol in the solution? Our given are temperatures. Water and ethylene glycol are at 115 degrees Celsius. Vapor pressure, water is 1085 torr. Partial pressure, ethylene glycol is 1.30 atmosphere, or when converted by 760 torr all over 1 atmosphere is 988 torr. Hint: in order to immediately know the solvent in this kind of problems, it is always the larger pressure value when we have 2. You can also look for context clues here. Moving on, what we need to find is the mole fraction of ethylene glycol. Solving it, deriving the main equation of Raoult's law in terms of mole fraction, we will have this. Solving it, deriving the main equation of Raoult's law in terms of mole fraction, we will have this. Plugging in our values and cancelling out torr units, we have 0.91x. But this is actually mole fraction of the solvent, water, and not ethylene glycol, the solute. We must remember that mole fractions of solute and solvent together is equal to 1. So by deriving it in terms of mole fraction solute, like this, we will know that 0.09x is the mole fraction of ethylene glycol.
Okay, let's try this one. Calculate the vapor pressure lowering delta P when 10.0 ml of glycerol C3H8O3 is added to 500.0 ml of water at 50 degrees Celsius. At this temperature, the vapor pressure of pure water is 92.5 torr and its density is 0.988 grams per milliliter. The density of glycerol is 1.26 grams per milliliter. Our given are volume of glycerol at 10.0 ml, volume of water is 500.0 ml, the temperature was 50 degrees Celsius, vapor pressure of water is 92.5 torr, the density of water is 0.988 milliliter, whereas density of glycerol is 1.26 milliliter. What we need to find is the vapor pressure lowering, which is delta or change in P. Now, we need to convert their volumes into grams and into moles. We can do this by multiplying their volumes to their densities. And then, to their molar masses in order to get our desired molar values. Let's first try glycerol. As shown here, cancelling out milliliter and grams while knowing that the molar masses is equated at 92.094 grams per mole. We now get 0.137 moles of glycerol present in that solution. For water, following the same steps as glycerol, cancel milliliters and grams having its molar mass at 18.015 grams per mole. We get 27.422 moles of water. Moving on, we can actually equate mole fraction like this. X sub n or m is equals to mole sub n or m all over mole sub n plus mole sub m, where n or m can either be the solute or the solvent, as long as the denominator is the entire solution. Thus, referring to the mole fraction of the solute, glycerol, we get 0.004971. Remember that we refer to vapor pressure lowering. We change the mole fraction of the solvent at X sub A in Raoult's law into the mole fraction of the solute. Thus, delta P is equal to the mole fraction of solute multiplied to the vapor pressure of the pure solvent. Plugging those values in, we arrived at 0.460 torr of vapor pressure lowered when the glycerol was added to the water.
Boiling point elevation is the next colligative property to discuss. This is an occurrence when the boiling point of the solution, mainly the solvent, to elevate or increase when a solute is added into it, usually non-volatile compounds. Its formula is as follows. Delta T sub B is equal to K sub B multiplied to M. Delta T sub B pertains to the boiling point elevation at degrees Celsius. I is the Van Hoff or the dissociation factor of the solute. K sub B is a constant, the molar boiling point constant of the solvent used at degrees Celsius all over molar. K sub B values are available in online sources or in textbooks, and you might need a reference along the way. M is basically the molality of the solution at molar units. We will also discuss now the later colligative property, the freezing point depression. Freezing point depression indicates that the freezing of the solution may need the solvent once more to depress or decrease when a non-volatile solute or substance is yet again added. Quite similar to the boiling point elevation formula, but with some changes of variables such as delta T sub F is equal K sub F multiplied to M. Delta T sub F is the freezing point depression at degrees Celsius. I is once more the Van Hoff or the dissociation factor of the solute. K sub F is another constant, the molar freezing point constant of the solvent used also at degrees Celsius all over molar. Same case, check some sources and references for this. M is yet again the molality of the solution at molar units. Let's check on this example. What is the molality of a solution dissolved in chloroform that boils at 62.8 degrees Celsius? The boiling point of chloroform is 62.2 degrees Celsius and its molar boiling point constant is 3.63 degrees Celsius per molar unit. Our given are boiling point of the solution at 62.8 degrees Celsius, boiling point of chloroform at 62.2 degrees Celsius, the molar boiling point constant of chloroform which is 3.63 degrees Celsius per molar unit. The boiling point elevation here is actually the boiling point of the solution subtracted from that of chloroform, so it is actually 0.6 degrees Celsius. The dissociation factor is assumed to be 1, so it is disregarded in the matter. What we need to find is the molality of the solution. Solving through it, we derive the formula of the boiling point elevation in terms of molality. Plugging in those respective values and cancelling out degrees Celsius, we arrive at 0.17 molar of the chloroform solution.
Next, let's check this out. You add 1 kg of ethylene glycol antifreeze or C2H6O2 to your carburetor. which contains 4,450 grams of water. What are the boiling and freezing points of the resulting solution? R given are 1 kilogram or 1,000 grams of ethylene glycol, the 4,450 grams or 4.450 kilogram of water. The dissociation factor of ethylene glycol is only 1, thus disregarding along the process. We can already solve the molar mass of ethylene glycol, which is at 62.068 grams per mole. What we need to find is both the new boiling and freezing points of this solution of water and ethylene glycol. Initially, we must convert first the mass of ethylene glycol into moles. We can do this by multiplying the mass with the factor of the molar mass of ethylene glycol, as seen here. We actually get 16.111 moles of ethylene glycol with a kilogram of its amount. We now move further in getting the molality of this antifreeze solution. We can get the molality by the amount of solute in moles all over the mass of the solvent in kilograms, which brings us here, giving us the molality at 3.620 molal of antifreeze solution. We can now answer this simultaneously, both via boiling and freezing points. Just to recapitulate, our dissociation factor is disregarded since it is only 1. The molar boiling point constant for water is 0.512 degrees Celsius over molal, and the molar freezing point constant of it is 1.86 degrees Celsius over molal. For the boiling point, we refer to the formula of its elevation. We plug in those respective values. We arrive that it will rise at 1.853 degrees Celsius. To get the actual boiling point, it is formed when we add the boiling point of the pure solvent in the boiling point elevation that we found, which gives us that the boiling point of the antifreeze solution to be 101.853 degrees Celsius. For the freezing point, it is roughly the same procedure a while ago. The formula of depression plugging in the corresponding values, we now know that it decreases at 6.733 degrees Celsius. Now for us to get the freezing point of this solution, we must subtract the actual freezing point of the solvent and the answer we got from the depression formula, which leads us to the freezing point of the antifreeze solution to be at negative 6.733 degrees Celsius.
Following that, let's have another take on this one. The boiling point of an aqueous solution is 102.5 degrees Celsius. What is the freezing point of the solution? Let us first have our assumptions. Since the solute is not specified and so is the molality, let us make the initial dissociation factor to be 1 as it should be non-volatile. We must also establish that the solvent is water given that it is aqueous. Moving on with our given, we have the solvent as water, the initial dissociation factor to be 1, the boiling point of that given aqueous solution to be 102.5 degrees Celsius. We can already find out its boiling point elevation as we subtract the boiling point of the aqueous solution to the actual boiling point of water at 100 degrees Celsius. We now get that the boiling point elevation is actually 2.5 degrees Celsius. We now also reminded that the molar boiling point and freezing point constants of water are 0.512 and 1.86 degrees Celsius over molar respectively. What we must find out is the freezing point of this aqueous solution. Referring to our boiling point elevation formula and derive it in terms of molality. We will now plug in those values, cancel degrees Celsius, and know that the molality of this aqueous solution is 4.883 molal of the aqueous solution. Now we go to the freezing point depression formula. We plug in again those corresponding values, cancel the molar units, and get that it is 9.082 degrees Celsius of the temperature decreased in that solution. In acquiring the freezing point of the solution, we must subtract the actual freezing point of water at 0 degrees Celsius to the value we got from the freezing point depression formula. We found out that the freezing point of the solution would be negative 9.082 degrees Celsius. In the moment, let's revisit the dissociation factor. We can actually try the factor to be assumed as 2, and still, following the same procedures, we roughly get the same answer at negative 9.08 degrees Celsius. This additionally indicates that any dissociation factor will do in this problem.
Finally, let's try this one, shall we? A solution of propylene glycol antifreeze in the coarse radiator has a freezing point of negative 20 degrees Celsius. What is the molarity of the solution? Our given are the freezing point of the antifreeze solution is negative 20 degrees Celsius. The dissociation factor to be 1 since it is only propylene glycol, so it is disregarded in our part. Next, the solvent of antifreeze solution is water. Thus, the freezing point is 0 degrees Celsius, which can be subtracted to the freezing point of this solution, which results to be 20 degrees Celsius, or freezing point depression. Water's molar freezing point constant to be 1.86 degrees Celsius over molality. What we need to find is the molality of the antifreeze solution. We can solve this by referring to our formula for freezing point depression and deriving in the terms of molality. Plugging in those values and cancelling out degrees Celsius, we simply get 10.753 molality of the antifreeze solution.
So, in a nutshell, we have discussed lessons and examples revolving around colligative properties. A colligative property is dependent on the ratio of the solute and solvent in a solution. We talk about three. First, the vapor pressure lowering. This property denotes that when we add a solute component in a solvent, it lowers its initial pressure. We can refer to the formula of Raoult's law at P sub A is equal to X sub A multiplied to P null sub A. Second, the boiling point elevation. This property indicates that when we add a non-volatile solute to a volatile solvent, it increases its initial boiling point. We can refer to this formula at delta T sub B is equal to K sub B multiplied to M. Lastly, the freezing point depression. The property shows that when we again add a non-volatile solute to a volatile solvent, it decreases its initial freezing point, and we can refer to this formula at delta T sub F is equal to K sub F multiplied to M. That's all, and thank you for watching.